Statistics module, mathematical statistics functions. Source code lib/statistics.py. This module provides functions for calculating mathematical statistics of numeric real valued data. The module is not intended to be a competitor to third-party libraries such as NumPy, SciencePy, or proprietary full-featured statistics packages aimed at professional statisticians such as Minitab, SAS, and MATLAB. It is aimed at the level of graphing and scientific calculators. Unless explicitly noted, these functions support integer, float, decimal, and fraction. Behavior with other types, whether in the numeric tower or not, is currently unsupported. Collections with a mix of types are also undefined and implementation dependent. If your input data consists of mixed types, you may be able to use map to ensure a consistent result. For example, map float in comma input data. Some data tests use NaN, not a number values, to represent missing data. Since NaNs have unusual comparison semantics, they cause surprising or undefined behaviors in the statistics functions that sort data or that count occurrences. The functions affected are median, median underscore low method, median underscore high method, median underscore grouped method, mode method, multi-mode method, and quantiles method. The NaN values should be stripped before calling this function. From statistics, import median. From math, import is NaN. From ITER tools, import filters false. Data is equal to 20.7 float NaN, comma 19.2, 18.3, comma float NaN, comma 14.4. Sorted data. This has surprising behavior. This median data. This result is unexpected. Some map is NaN data. Number of missing values 2. Clean is equal to list filter false is NaN. Filter false is NaN data. Strip NaN values. List is equal to clean. Sorted clean. Sorting now works as expected. 14.4, 18.3, 19.2, 20.7. Median clean. The result is now well defined. New directory. Statistics module. New example 1. Sorted data. Print sorted data. .7 NaN, 14.4, 18.3, 19.2 NaN. This is not correct, so we have to clean, remove these NaNs. So median data, this is also an expected result, so print median data. This will give unexpected result, that is 16.35. So now fix this issue by removing NaNs from the list. So some map is NaN. Print some map is an data 2 is map is an 2 number of missing values. Now clean. print clean the data. So list filter false is NaN. Filter false, filter filter any value that is false, that is for which is NaN is false. So print clean. Now it will remove NaNs, and then sorted clean. Now this will also work. Now sort will work. Print sorted clean. This is now working as expected, and median will be now working as well. Median will also work. Print 18.75. Averages and measures of central location. These functions calculate an average or typical value from a population or sample. Mean, arithmetic mean, average of data. F mean, fast floating point arithmetic mean with optional weighting. Geometric mean of data. Harmonic mean of data. Median of data. Median low median of data. Median high median of data. Median underscore grouped, median or 50th percentile of grouped data. Mode, single mode, most common value of discrete or nominal data. Multimode, list of modes, most common values of discrete or nominal data. Quantiles, divide data into intervals with equal probability. Measures of spread. These functions calculate a measure of how much the population or sample tends to deviate from the typical or average values. PST-DEV, population standard deviation of data. P-variance, population variance of data. STD-EV, sample standard deviation of data. Variance, sample variance of data. Statistics for relations between two inputs. These functions calculate statistics regarding relations between two inputs. Covariance, sample covariance for two variables. Correlation, Pearson and Spearman correlation coefficient. Linear regression, slope and intersect for simple linear regression. Function details. Note, the functions do not require the data given to them to be sorted. However, for reading convenience, most of the examples show sorted sequences. Statistics.mean data. Return the sample arithmetic mean of data, which can be a sequence or iterable. The arithmetic mean is the sum of the data divided by the number of data points. It is commonly called the average, although it is only one of many different mathematical averages. It is a measure of the central location of the data. If data is empty, statistical error will be raised. Some examples of use: mean, Python. Example 2. Mean, from statistics import mean. Mean M, print M. Run. 2.8. Mean this, print mean this. 2.65. From fractions import fraction as f. Mean f37 f12. Mean is equal to n print m 13 by 21. From decimal import decimal as d, mean d 0.5, d 0.75, this. Note: the mean is strongly affected by outliers and is not necessarily a typical example of the data points. For a more robust, although less efficient, measure of central tendency, see median. The sample mean gives an unbiased estimate of the true population mean, so that when taken on average over all the possible samples, mean sample converges on the true mean of the entire population. If data represents the entire population rather than a sample, then mean data is equivalent to calculating the true population mean or mu. Statistics.f mean data Bayes is equal to none. Convert data to floats and compute the arithmetic mean. This runs faster than the mean function and it always returns a float. The data may be a sequence or iterable. If the input data set is empty, raises statistics error. F mean. Print F mean. Import comma F mean. Run 4. Optional weighting is supported. For example, a professor assigns a grade for a course by weighting quizzes at 20%, homework at 20%, a mid-term exam at 30%, and a final exam at 30%. Grades this, weighs this, and F mean. Is equal to F mean. Print F mean. Run. 87.6. If Bayes is applied, it must be the same length as the data or a value error will be raised. Statistics.geometric mean data. Convert data to floats and compute the geometric mean. The geometric mean indicates the central tendency or typical value of the data using the product of values as opposed to the arithmetic mean, which uses their sum. Raises statistical error if the input dataset is empty, if it contains 0, or if it contains a negative value. The data may be a sequence or iterable. No special efforts are made to achieve exact result. However, this may change in the future. Round. Print round geometric mean. From statistics, import geometric mean. 36 point. Statistics.harmonic mean data Bayes is equal to none. Return the harmonic mean of data, a sequence or iterable of real valued members. If weights is omitted or none, then equal weighting is assumed. The harmonic mean is the reciprocal of the arithmetic mean of the reciprocals of the data. For example, the harmonic mean of 3 values a, b, and c will be equivalent to 3 by 1 by a plus 1 by b plus 1 by c. If one of the values is 0, the result will be 0. The harmonic mean is a type of average, a measure of the central location of data. It is often appropriate when averaging ratios or rates. For example, speeds. Suppose a car travels 10 km at 40 km per hour, then another 10 km at 60 km per hour. What is the average speed? Harmonic mean 40-60. From statistics, import harmonic mean. Print harmonic mean. 40-60. 48.0. Suppose a car travels 40 km per hour for 5 km, and when traffic clears speeds up to 60 km per hour for the remaining 30 km of the journey. What is the average speed? Harmonic underscore mean 40/60. Weights is equal to waist weights is equal to 510 530. Print. 56.40. Statistics error is raised if data is empty, any element is less than 0, or if the weighted sum is not positive. The current logarithm algorithm has an early out when it encounters a 0 in the input. This means that the subsequent inputs are not tested for validity. This behavior may change in the future. Statistics.median data. Return the median middle value of numeric data using the common mean of middle 2 method. If data is empty, statistics error is raised. Data can be a sequence or iterable. The median is a robust measure of central location and is less affected by the presence of outliers. When the number of data points is odd, the middle data point is returned. Median 135. Example 3. From statistics, import median. Print median. Median 135. When the number of data points is even, the median is interpolated by taking the average of the two middle values. Median 3 and 5 8 divided by 2. 4.0. This is suited for when your data is discrete and you don't mind that the median may not be an actual data point. If the data is ordinal, supports order operations but not numeric, doesn't support addition, consider using median low or median high instead. Statistics.median no low data. Return the low median of numeric data. If data is empty, statistics error is raised. Data can be sequence or iterable. The low median is always a member of the data set. When the number of data points is odd, the middle value is returned. When it is even, the smaller of two middle values is returned. Median low, median low, comma, median low, comma, median high. Print this, and median low, print this. Let's see. Low is 3. Okay. Use the low median when your data are discrete and you prefer to the median to be the actual data point rather than interpolated. Statistics.median high data. Return the high median of data. If data is empty, statistics error is raised. Data can be sequence or iterable. The high median is always a member of the data set. When the number of data points is odd, the median middle value is returned. When it is even, the larger of the two middle values is returned. Print high, print this time. High 5 3 3. Oh, median high. Use the high median when your data are discrete and you prefer the median to be the actual data point rather than interpolated. Statistics dot median underscore grouped data interval is equal to 1. Return the median of grouped continuous data calculated as the 50th percentile using interpolation. If data is empty, statistics error is red. Data can be a sequence or iterable. Median grouped, print median grouped, run 52.5. In the following example, the data are rounded so that each value represented the midpoint of data classes. Example 1 is the midpoint of the class 0.5, 1.5. 2 is the midpoint of 1.5 to 2.5. 3 is the midpoint for 2.5 to 3.5, etc. With the given data given, the middle value falls somewhere in the class 3.5, 4.5, and interpolation is used to estimate it. Median, let's print it. Median group and print it. 3.7. Optional argument interval represents the class interval and defaults to 1. Changing the class interval naturally will change the interpolation. Median grouped 1 through 7 interval is equal to 1. Print interval is equal to 1 and print interval is equal to 2. Print median interval is equal to 2. Let's run it. 2.25. The function does not check whether the data points are at least interval apart. See Python implementation detail. Under some circumstances, median grouped may coerce data points to floats. This behavior is likely to change in the future. Statistics for the behavioral sciences, Frederick J. Gravatar and Larry B. Volnia, 8th edition. The SS median function in the genomic spreadsheet, including this discussion. Statistics.mode data. Return the single most common data point from discrete or nominal data. The mode, when it exists, is the most typical value and serves as a measure of central location. If there are multiple modes with the same frequency, returns the first one encountered in the data. If the smallest or largest of those is desired, instead use mean multi-mode data or max multi-mode data. If the input data is empty, statistics error is raised. Mode assumes discrete data and returns a single value. This is the standard treatment of the mode as commonly taught in the school. Mode. Let's print mode, comma mode, print, and then 3, mode 3, 1, 2, 3, 4, highest. The mode is unique in that it is only statistics in this package that also applies to nominal non-numeric data. Mode of this, print mode of this, red, blue, blue, red, green, red, red, red. Statistics.multimode data. Return a list of the most frequently occurring values in the order they were first encountered in the data. Will return more than one result if there are multiple modes or an empty list if the data is empty. Multi-mode. Let's do the example 4 from statistics. Import multi-mode, print multi-mode. Let's run it. BDF 4 times, all are 4 times, that's why it is. Statistics.pst data mu null. Return the population standard deviation, the square root of the population variance, CP variance for arguments and other details. PST dev, print PST dev, population variance 0.98. Statistics.p variance data mu is equal to none. Return the population variance of data, a non-empty sequence or iterable of real valued members. Variance or second moment about the mean is a measure of the variability, spread or dispersion of data. A large variance indicates that the data is spread out. A small variance indicates it is clustered closely around the mean. If the optional second argument mu is given, it is typically the mean of the data. It can also be used to compute the second moment around a point that is not the mean. If it is missing or non-default, the arithmetic mean is automatically calculated. Use this function to calculate the variance from the entire population. To estimate the variance from a sample, the variance function is usually a better choice. Raises statistics error if data is empty. Data p variance data. Let's do this. P variance. So print the p variance data. Run 1.25. If you have already calculated the mean of your data, you can pass it as the optional second argument mu to avoid calculation. Mu mean data, p variance data mu 1.25. Decimals and fractions are supported. From decimal, import decimal as d, p variance d, 27.5 d, 30.25, 30.25, 34.5, 41.75 decimal 20. From fractions, import fractions as f, p variance f14, f54, f12. When called with the entire population, this gives the population variance. This when called on a sample instead, this is the biased sample variance as square, also known as a variance with n degree of freedom. If you somehow know the true population mean mu, you may use this function to calculate the variance of a sample, giving the known population mean as the second argument. Provided the data points are a random sample of the population, the result will be an unbiased estimate of the population variance. Statistics.stdev data x bar is equal to none. Return the sample standard deviation, the square root of the sample variance. See variance for arguments and other details. Stddev standard deviation. Stddev standard deviation. Print stddev none. Statistics.variance data x bar is equal to none. Return the sample variance of data and iterable of at least two real valued numbers. Variance or second moment about the mean is a measure of the variability, spread or dispersion of data. A large variance indicates that the data is spread out. A small variance indicates it is clustered closely around the mean. If the optional second argument x bar is given, it should be the mean of data. If it is missing or non-default, the mean is automatically calculated. Using this function when your data is a sample from a population to calculate the variance from the entire population. See p variance. Raises statistics error if data has fewer than two values. Data is equal to this variance data. If you have already calculated the mean of your data, you can pass it as the optional second argument x bar to avoid recalculation. Mean data, variance data m. This function does not attempt to verify that you have passed the actual mean as x bar. Using arbitrary values of x bar can lead to invalid or impossible results. Decimal and fractions values are supported too. This is the sample variance s square with Bessel correction, also known as variance with n-1 degree of freedom. Provided that the data points are representative, independent and identically distributed, the result should be an unbiased estimate of the true population variance. If you somehow know the actual population mean mu, you should pass it to the variance function as the mu parameter to get the variance of sample. Statistics.quantils data asterisk n is equal to for method is equal to exclusive. Divide data into n continuous intervals with equal probability. Return a list of n minus 1 cut points separating the intervals. Set n to 4 for quartiles, the default. Set n to 10 for deciles. Set n to 100 for percentiles, which gives the 99 cuts points that separate data into 100 equal sized groups. Raises statistics error if n is not least 1. The data can be any iterable containing sample data. For meaningful results, the number of data points in data should be larger than n. Raises statistics error if there are not at least two data points. The cut points are linearly interpolated from the two nearest data points. For example, if a cut point falls one third of the distance between two sample values 100 and 112, the cut point will evaluate to 104. The method for computing quantiles can be varied depending on whether the data includes or excludes the lowest and highest possible values from the population. The default method is exclusive and is used for data sampled from a population that can have more extreme values than found in the samples. The portion of the population falling below the ith of m sorted data points is computed as I by m plus 1. Given 9 sample values, the method sorts them and assigns the following percentiles: 10%, 20%, 30%, 40%, 50%, 60%, 70%, 80%, 90%. Setting the method to inclusive is used for describing population data or for samples that are known to include the most extreme values from the population. The minimum value is data is treated as the 0th percentile and the maximum value is treated as the 100th percentile. The proportion of the data population falling below the ith of m sorted data points is computed as I minus 1 m minus 1. Given 11 sample values, the method sorts them and assigns the following percentiles: 0th, 10th and 100th. Decile cut points for empirically sampled data. Data points round q1 for q in quantiles data n is equal to 10. Statistics.covariance xy slash return the sample covariance of two inputs xy. Covariance is a measure of the joint variability of two inputs. Both inputs must be of the same length, no less than 2, otherwise statistics error is raised. X is equal to this, y is equal to this, covariance x comma y 0.75, z is equal to this, covariance xz minus 7.5, covariance zx this. Statistics correlation x y slash star method is equal to linear. Return the Pearson's correlation coefficient for two inputs. Pearson's correlation coefficient are text values between minus 1 and plus 1. It measures the strength and the direction of a linear relationship. If method is ranked, computes Spearman's rank correlation coefficient for two inputs. The data is replaced by ranks. Tiers are averaged so that equal values receive the same rank. The resulting coefficient measures the strength of a monotonic relationship. Spearman's correlation coefficient is appropriate for ordinal data or for continuous data that does not meet the linear proportion requirement for Pearson's correlation coefficient. Both inputs must be of the same length, no less than 2, and need not to be constant, otherwise statistics error is raised. Example with Kepler's law of planetary motion. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus and Neptune. Orbital period 88, these are period number of days. Distance from Sun million kilometers, so that a perfect monotonic relationship exists. Correlation orbital period distance from Sun method is equal to ranked 1.0. Observe that a linear relationship is imperfect. Round correlation orbital period distance from Sun 4 0.9882. Demonstrate Kepler's third law. There is a linear correlation between the square of the orbital period and the cube of the distance from the Sun. Period squared, p square for p in orbital period. Distance cubed, d into d into d for d in distance from Sun. Round correlation period squared distance cubed for 1. Statistics linear regression x y slash star proportional is equal to false. Return the slope and intercept of simple linear regression parameters estimated using ordinary least squares. Simple linear regression describes the relationship between an independent variable x and a dependent variable y in terms of this linear function. y is equal to y is equal to slope into x plus intercept plus noise, where slope and intercept are the regression parameters that are estimated and noise represents the variability of the data that was not explained by the linear regression. It is equal to the difference between predicted and actual values of the dependent variable. Both inputs must be of the same length, no less than 2, and the independent variable x cannot be constant, otherwise a statistics error is raised. For example, we can use the release dates of the Monty Python films to predict the cumulative number of Monty Python films that would have been produced by 2019, assuming that they had kept the pace. Here, these films total this slope intercept linear regression year so round slope into 2019 intercept 16. If proportional is true, the independent variable x and independent variable y are assumed to be directly proportional. The data is fed to a line passing through the origin. Since the intercept will always be 0, 0, the underlying linear function simplifies to y is equal to slope into x plus noise. Continuing the example from correlation, we'll look to see how well a model based on a major planets can predict the orbital distances for dwarf planets. Model is equal to linear regression period is squared, distance cubed, proportional is equal to 2, slope is equal to model dot slope. Dwarf planets Pluto, Eris, McMahon, Haumea, Ceres. Orbital periods this predicted dist math.cbrt slope into p into e p for p in orbital periods. List map round predicted distance. Exceptions. A single exception is defined. Exception statistics dot statistics error subclass of value error for statistics related exception. Normal dist object. Normal dist is a tool for creating and manipulating normal distributions of a random variable. It is a class that treats the mean and standard deviation of data measurements as a single entity. Normal distributions arise from the central limit theorem and have a wide range of applications in statistics. Class statistics dot normal dist mu 0.0 sigma 1.0. Return a new normal dist object where mu represents the arithmetic mean and sigma represents the standard deviation. If sigma is negative, raises statistics error. Mean, a read-only property for the arithmetic mean of a normal distribution. Median, a read-only property for the median of a normal distribution. Mode, a read-only property of the mode of a normal distribution. STDU, a read-only property for the standard deviation of a normal distribution. Variance, a read-only property of the variance of a normal distribution equal to the square of the standard deviation. Class method. From samples data, make a normal distribution instance with mu and sigma parameters estimated from the data using f mean and stdev standard deviation. The data can be any iterable and should consist of values that can be converted to type float. The data does not contain at least two elements, raises statistics error because it takes at least 1 point to estimate a central value and at least 2 points to estimate dispersion. Samples n in star seed is equal to none. Generates n random samples for a given mean and standard deviation. Return a list of float values. If seed is given, creates a new instance of the underlying random number generator. This is useful for creating reproducible results even in multi-threading context. PDFX. Using a probability density function, PDF compute the relative likelihood that a random variable x will be near the given value x. Mathematically, it is the limit of the ratio px less than equal to x less than x plus dx by dx as dx approaches 0. The relative likelihood is computed as the probability of a sample occurring in a narrow range divided by the width of the range. Hence, the word density, since the likelihood is relative to other points, its value can be greater than 1.0. CDFX. Using a cumulative distribution function, compute the probability that a random variable x will be less than or equal to x. Mathematically, it is written px less than equal to x. INV underscore CDFP. Compute the inverse cumulative distribution function, also known as the quantile function or the percentile point function. Mathematically, it is written x px less than equal to x equal to p. Finds the value x of the random variable x such that the probability of the variable being less than or equal to the value equals the given probability p. Overlap other measures the agreement between two normal probability distributions, returns a value between 0.0 and 1.0, giving the overlapping area for the two probability density functions. Quantiles n is equal to 4. Divide the normal distribution into n continuous intervals with equal probability. Returns a list of n minus 1 cut points separating the intervals. Set n is n to 4 for quartiles, the default. Set n to 10 for deciles. Set n to 100 for percentiles, which gives the 99 cut points that separate the normal distribution into 100 equal sized groups. Z score x. Compute the standard score describing x in terms of the number of standard deviations above or below the mean of the normal distribution. X minus mean divided by standard deviation. Instances of normal distribution support addition, subtraction, multiplication, and division by a constant. These operations are used for translation and scaling. For example, temperature February, normal distribution 2.5 Celsius. Temperature February into 9 by 5 plus 32 Fahrenheit. Normal distribution mu 41.0 sigma 4.5. Dividing a constant by an instance of normal distribution is not supported because the result wouldn't be normally distributed. Since normal distributions arise from additive effects of independent variables, it is possible to add and subtract two independent normally distributed random variables represented as instances of normal For example, birth weights, normal distribution from samples. These drug effects, normal distribution. This combined birth weights plus drug effects. Round combined dot mean 1 3.1. Round combined dot standard deviation 1. Normal distribution examples and recipe. Class probability problems. Normal distribution really solves classic probability problems. For example, given historical data for SAT exams showing that scores are normally distributed with a mean of 1060 and a standard deviation of 195, determine the percentage of students with test scores between 1100 and 1200 after rounding to the nearest whole number. Set normal distribution 1060 195. Fraction set.cdf 1200 plus 0.5 minus set.cdf 1100 minus 0.5. Round fraction into 100.001 18.4. Find the quartiles and deciles for the set score. List map round set.quantiles. List map round set.quantiles n is equal to 10. Monte Carlo inputs for simulation. To estimate the distribution for a model isn't easy to solve analytically. Normal distribution can generate input samples for Monte Carlo simulation. Diff model XYZ return 3x plus 7xy minus 5y divided by 11z. N is equal to 1 lakh. X is equal to normal distribution 10 2.5 samples and seed this. Y is equal to normal distribution 15 1.75 samples this. Z is equal to normal distribution 50 1.25 samples this. Quantiles map model XYZ. Approximating binomial distribution. Normal distribution can be used to approximate binomial distributions when the sample size is large and when the probability of a successful trial is near 50%. For example, an open source conference has 750 attendees and two rooms with 500% capacity. There is a talk about Python and another about Ruby. In previous conferences, 65% of the attendees prefer to listen to Python talks, assuming the population preferences haven't changed. What is the probability that the Python room will stay within its capacity limit? N is equal to 750, P is equal to 0.65, Q is equal to 1 minus P, K is equal to 500. Approximation using the cumulative normal distribution. From math, import SQRT. From normal distribution, ME is equal to NP sigma is equal to square root of NPQ dot CDF K plus 0.54. This exact solution using the cumulative binomial distribution. From math, import com fsum round fsum com nr into pr into q square n minus r times for r in range k plus 1 for approximation using a simulation. From random, import seed binomial variate seed. This mean binomial variate np less than equal to k for I in range this. Naive Bayesian classifier. Normal distributions commonly arise in machine learning problems. Wikipedia has a nice example of a naive Bayesian classifier. The challenge is to predict a person's gender from measurements of normally distributed features including height, weight, and foot size. We are given a training data set with measurements for 8 people. The measurements are assumed to be normally distributed, so we summarize the data with normal distribution. This one. Next, we encounter a new person whose feature measurements are known but whose gender is unknown. ST 6.0, weight 130, FS 8. Starting with a 50% prior probability of being male or female, we compute the posterior as the prior times the product of likelihood for the feature measurements given the gender. Prior male 0.5, prior female 0.5, posterior male, prior male into height male dot pdf st into weight male pdf wt into foot size male dot pdf fs. Posterior female is the same. The final prediction goes to the largest posterior. This is known as the maximum posteriority or map. Male if posterior male greater than posterior female, else female. Kernel density estimation. It is possible to estimate a continuous probability density function from a fixed number of discrete samples. The basic idea is to smooth the data using a kernel function such as a normal distribution, triangular distribution, and uniform distribution. The degree of smoothing is controlled by a scaling parameter h, which is called the bandwidth. Diff KDE normal sample h create a continuous probability density function from a sample. Kernel h is equal to normal dist 0.0 h dot pdf. N is equal to length sample diff pdf x returns sum kernel underscore h x minus xi for xi in sample divided by n return pdf. Wikipedia has an example where we can use the KDE normal recipe to generate and plot a probability density function estimated from a small sample. Sample is equal to this, f hat KDE normal sample h is equal to this, and x array I by 100 for I in range minus 75 1100, y array f hat x for x in x. The points in x array and y array can be used to make a PDF plot. Thank you.